1 million kilometers of jets shooting toward the sun. That is what should not be possible. When comets pass close to our star, they shed material away from it, blown by radiation pressure and solar wind, like cosmic windsocks showing which way the energy flows. But new images captured just days ago of 3IATLAS, an object that arrived here from another star system, show something that breaks the rules. Multiple jets streaming sunward, defying the physics we thought we understood. One of those jets extends nearly 1 million kilometers into space, punching through solar wind, traveling at 400 kilometers per second. And this is happening while the object is hemorrhaging mass at rates that suggest something catastrophic, something explosive, something that might consume the entire nucleus before we fully understand what we are looking at. Is this the final act of a dying comet torn apart by solar heating? Or are we witnessing controlled deceleration, an engineered object executing the braking maneuver it was designed for millions of years ago? Stay with me until the end, because what astronomers are discovering about this visitor is rewriting our understanding of interstellar objects and raising questions that make even the most skeptical scientist pause. If this mystery has you hooked, hit like and subscribe so you do not miss what comes next. Comment where you are watching from and what you think is really happening with 3IATLAS. And if you want to support this investigation, share this video. Every share helps us keep exploring these cosmic enigmas. Thanks for being here. Something appeared in Earth's morning sky on November 8th, 2025, that no one was prepared for. 3 astronomers, Michael Jaeger from Austria, Gerald Riemann from Namibia, and Emmanuel Prosperi from Australia, independently aimed their telescopes at a moving speck of light low on the horizon, fighting twilight and a bright moon and miles of thick atmosphere. They captured 28 separate exposures, 24 through a green filter, 2 red, 2 blue, each frame lasting 35 seconds. They stacked those images together, pulling signal from noise, extracting details the human eye could never perceive alone. What emerged from that processing made astronomers around the world lean forward and whisper a single word: impossible. The object has a name: 3IATLAS, the third confirmed interstellar visitor ever detected by humanity, discovered on July 1st, 2025, by the Atlas Survey telescope in Chile. For months, we tracked it as it plunged toward the sun, watching it brighten and develop a tail like any normal comet. We thought we understood what it was: an icy refugee from another stellar system, heated by our sun, outgassing in predictable ways. We were wrong. The November 8th image shows at least 7 distinct jets of material erupting from the nucleus, streaming into space in multiple directions. Not 1 jet, not 2, 7. Some stretch away from the sun as expected, blown by radiation pressure, but others, impossibly, point toward the sun. They form a network, a structure, almost a symmetry that natural random outgassing should not produce. The observers captured this while 3IATLAS was just 29 degrees from solar glare, only 7 to 10 degrees above the horizon, conditions where faint details vanish into atmospheric haze and twilight glow. And still, the jets appeared, crisp and undeniable and structured. 2 days later, on November 9th, British astronomers Michael Buchner and Frank Niebling captured another image using different equipment. What they revealed was even more staggering. The sunward jets extend approximately 950,000 kilometers into space, nearly 1 million kilometers of material streaming in the wrong direction. The tail pointing away from the sun measures 2.85 million kilometers, 3 times longer. Together, these structures span distances that dwarf anything the Hubble Space Telescope had observed from 3IATLAS earlier in the year, when the comet was farther from the sun and less active. You need to understand the scale here. Earth's diameter is about 12,700 kilometers. The moon orbits roughly 384,000 kilometers away. The sunward jet from 3IATLAS extends 2.5 times the Earth-Moon distance. This is not a puff of gas. This is sustained, violent, directional ejection of material on scales that make our entire planet look insignificant. Avi Loeb, the Harvard astrophysicist who has made a career asking uncomfortable questions about interstellar objects, analyzed these images and published something that should make you pause. He calculated that the mass density in the anti-tail jets, those sunward-pointing structures, is approximately 1 million times greater than the surrounding solar wind. The solar wind moves at 400 kilometers per second, a hurricane of charged particles blasting outward from the sun's corona. For material to point sunward through that wind, to maintain coherent jet structure against forces pushing it the opposite direction, requires either extraordinary physics or something actively controlling the flow. Given that a large number of jets appear in many directions, Loeb wrote, the reported non-gravitational acceleration of 3IATLAS requires much more than 10 to 20% of its initial mass to have been ejected near perihelion. Read that again. This object is losing more than 1/5 of its total mass. It reached closest approach to the Sun, called perihelion, on October 30th, 2025, passing within 1.4 astronomical units, just inside Mars's orbit. Since then, it has been erupting, hemorrhaging material, tearing itself apart or executing a maneuver so energetic it might not survive. Why would a comet shed that much mass? Natural comets lose material through sublimation, where solar heat turns surface ice directly into gas without passing through a liquid phase. Typical mass loss rates are measured in tons per second, enough to create visible tails but not enough to threaten the nucleus integrity. Losing 10, 20, perhaps even 30% of total mass near perihelion suggests something catastrophic. Either the comet is fragmenting, cracking apart under thermal stress and rotational forces, or it is doing something deliberate, using its own material as propellant in a way that requires consuming the structure itself. Fragmentation is not unheard of. Comet Shoemaker-Levy 9 broke into 21 pieces before crashing into Jupiter in 1994. Comet Lineaire disintegrated in 2000 as it approached the Sun. Thermal stress, tidal forces, rapid rotation, all these can tear a loosely bound rubble pile apart. But fragmented comets produce chaotic debris clouds, not organized multi-jet structures. They dissolve into diffuse halos, not crisp streamers, extending millions of kilometers in specific directions. The images show no evidence of fragmentation. The nucleus appears intact, a single central condensation surrounded by the jets. Whatever is producing this activity is not random destruction. It is structured release. And that structure is what makes astronomers uncomfortable, because structure implies either composition and geometry we do not understand, or intent. The timing is also critical. Perihelion happened on October 30th. The dramatic images started appearing a week later, on November 8th and 9th, as 3IATLAS emerged from solar conjunction, that brief period when an object is too close to the Sun in Earth's sky to observe. During conjunction, the comet was hidden in solar glare, baking under maximum radiation. What happened during those hidden days? Did activity ramp up gradually, or did something trigger an explosive outburst? We do not know because we could not watch. By November 10th and 11th, more images started arriving. The Virtual Telescope project in Italy captured 3IATLAS showing a clear ion tail, a stream of ionized gas glowing as solar ultraviolet light strips electrons from molecules. The tail stretched at least 0.7 degrees across the sky, visible even with the comet just 14 degrees above the horizon and a 6.1% illuminated moon washing out the background. The anti-tail was also visible, pointing in the opposite direction, creating the visual paradox of a comet with two tails streaming in opposite directions simultaneously. This is rare, but not unprecedented. Several solar system comets have shown anti-tails, structures created when large dust grains lag behind the nucleus in its orbit and appear to point sunward due to projection effects when viewed from Earth at specific angles. But the sheer prominence and density of 3IATLAS's anti-tail jets set it apart. These are not faint wisps, visible only in carefully processed images. These are bright, coherent structures detectable under terrible observing conditions, which means they contain enormous amounts of material moving in directions that defy simple explanations. Why 7 jets? Why this specific number? Why this configuration? Natural sublimation occurs at active regions on the nucleus surface where volatile ices are exposed to sunlight. A spinning nucleus with multiple active vents could produce multiple jets as different regions rotate into sunlight. But 7 jets arranged in what appears to be a network is unusual. Statistically improbable, though not impossible. It requires a very specific distribution of ice deposits, a particular spin axis orientation, and geometric alignment with our viewing angle from Earth. Or it requires nozzles, thruster ports arranged around a hull, a probe using its own material as propellant, ejecting it in controlled patterns to adjust velocity and trajectory as it passes through the inner solar system. 7 thrusters would provide redundant vector control, the ability to rotate and maneuver in 3-dimensional space without complex gimbal systems. Fire all 7 and you produce braking thrust. Fire subsets in specific combinations and you adjust orientation. This is speculation, but it is not absurd speculation. We build spacecraft with multi-thruster configurations routinely. The question is whether nature can mimic that pattern or whether we are looking at something engineered. The November 8th and 9th images do not answer that question. They simply make it impossible to ignore. 3IATLAS was not supposed to exist. Not in the sense that interstellar objects are impossible, we have found 2 others before this, but in the sense that everything about its discovery and trajectory marks it as extreme. The most dynamically unusual object ever recorded passing through our solar system, a visitor that challenges our comfortable models of how these objects should behave. The story begins on July 1st, 2025, when the Atlas Survey Telescope in Rio Hurtado, Chile, flagged a faint moving object in the constellation Sagittarius. Atlas, the asteroid terrestrial impact last alert system, scans the sky nightly searching for near-Earth asteroids that might threaten our planet. It finds thousands of objects, most of them boring rocks tracing ordinary orbits. But this one moved differently, too fast. The trajectory did not close into an ellipse around the Sun. It was hyperbolic, an open curve arriving from interstellar space and destined to leave again after a brief swing past our star. Within hours of the discovery, astronomers around the world began follow-up observations. The Zwicky Transient Facility in California found pre-discovery images from June 28th and 29th, confirming the object existed before Atlas spotted it. Additional images from June 14th through 21st emerged from archival searches. Atlas itself had observed the object on June 25th through 29th without recognizing it as unusual because it was too faint and moving too slowly at that distance. Only as it approached and brightened did the motion become unmistakable. By July 2nd, the Minor Planet Center, the international clearinghouse for asteroid and comet discoveries, announced the finding and assigned it the designation 3IATLAS. The 3I marks it as the 3rd confirmed interstellar object, following 1I, Oumuamua, in 2017, and 2I, Borisov, in 2019. The center also gave it a secondary designation, C, 2025, N1, Atlas, classifying it as a comet. Within days, 122 observations from 31 different observatories had been collected, and the orbit was calculated precisely. The numbers were staggering. 3IATLAS entered the solar system on a hyperbolic trajectory with an orbital eccentricity greater than 1, meaning it is not bound to the Sun and will escape back into interstellar space after perihelion. Its hyperbolic excess velocity, the speed it retains after escaping the Sun's gravity, is the highest ever measured for an interstellar visitor. This object is moving fast, very fast. At perihelion, it reached approximately 68 kilometers per second relative to the Sun. Based on its trajectory, astronomers suspect 3IATLAS may be extraordinarily old. Calculations suggest it could be 3 billion years older than the solar system itself, making it possibly 7.6 billion years old. It formed in a stellar nursery around another star before our Sun even existed, before Earth was a glowing ball of molten rock. It has been wandering the galaxy for eons, drifting through the interstellar medium, surviving radiation and cosmic ray bombardment, until by chance, or design, it fell into our solar system. Early observations suggested it was behaving like a normal comet. By mid-July, it had brightened to magnitude 16, faint but detectable by amateur telescopes with long exposures. Spectroscopy revealed a faint coma, a hazy cloud of gas and dust surrounding the nucleus. It was outgassing, releasing material as solar heat began sublimating surface ice. Nothing about this seemed unusual. Astronomers classified it as an interstellar comet, similar to 2I, Borisov, and moved on with routine monitoring. But then came the James Webb Space Telescope observations. On August 6, 2025, Webb turned its near-infrared spectrograph toward 3IATLAS and captured detailed spectra of its coma. The results, announced by NASA on August 25th, were stunning. The comet showed an exceptionally high ratio of carbon dioxide to water, approximately 8:1. Most solar system comets have ratios closer to 110 or 120, with water ice dominating. Carbon dioxide is present but secondary. 3IATLAS flipped that ratio, showing among the highest carbon dioxide abundances ever measured in any comet. This was the first hint that something was different. Carbon dioxide ice sublimates at much lower temperatures than water ice. It can drive activity when a comet is still far from the Sun, beyond Mars's orbit, where water ice remains frozen. High carbon dioxide content means the comet can be extraordinarily active, producing jets and tails at distances where other comets are dormant. It also suggests a different formation environment, a stellar nursery colder and more carbon-rich than the region where our solar system's comets formed. NASA's Transiting Exoplanet Survey satellite, TESS, reviewed its archival data and found something even more surprising. Images from May 7, 2025, nearly 2 months before 3IATLAS was officially discovered, showed signs of cometary activity. At that time, the object was approximately 6.4 astronomical units from the Sun, beyond Jupiter's orbit, where most comets are inactive. But 3IATLAS was already outgassing, already developing a faint coma, driven by sublimating carbon dioxide that began warming even at those enormous distances. As the comet continued its approach through August and September, observers noted that it remained remarkably steady. No outbursts, no sudden flares, just gradual brightening as solar heating increased. It moved from Sagittarius into Ophiuchus, then into other constellations along the ecliptic, tracing its path toward perihelion on October 30th. By late September, it had become too close to the Sun in Earth's sky to observe from the ground. It vanished into solar glare for nearly 3 weeks, hidden during the most critical phase when solar heating reached maximum and activity should peak. During solar conjunction, on October 21st, the GOES-19 weather satellite, positioned above Earth to monitor clouds and storms, happened to capture an image of 3IATLAS. Weather satellites are not designed for astronomy, but they can detect bright objects near the Sun. The image confirmed the comet was still intact, still active, brightening as expected. But details were impossible to resolve. We had to wait until it emerged from conjunction in early November to see what had happened. When it reappeared, everything had changed. The quiet, steady comet had erupted. The morning of November 8, 2025, brought the first clear views of 3IATLAS after perihelion. Observers worldwide knew this was the critical window. The comet was emerging from behind the Sun, moving back into pre-dawn skies where Earth-based telescopes could target it. The question was what state it would be in. Would it have fragmented from thermal stress? Would it show increased activity? Would it even still exist? Michael Jaeger in Austria set his telescope, tracking the coordinates calculated from the comet's known orbit. The object was low, just 7 degrees above the horizon, barely clearing the trees and buildings that block his eastern view. Twilight was approaching, the sky brightening as the Sun prepared to rise. The moon, more than half full, glared from higher in the sky, washing out faint stars. These were awful conditions for astrophotography. But comets do not wait for ideal observing geometry. Simultaneously, Gerald Riemann in Namibia and Emmanuel Prosperi in Australia aimed their own equipment at the same target. Different continents, different telescopes, different cameras. If they all saw the same thing, it would be real, not an artifact of a single instrument or processing error. They began capturing exposures. 35 seconds each, filter wheels rotating between green, red, and blue. 24 green, 2 red, 2 blue. Nearly 15 minutes of total exposure time accumulated photon by photon. When Jaeger stacked his images and applied processing to enhance faint details, the structure leapt out. A bright central condensation, the nucleus itself, surrounded by an enormous halo extending nearly 500,000 kilometers, roughly 5 arc minutes across the sky. That halo is bigger than Jupiter, bigger than Saturn, But the halo was expected. What was not expected were the jets. 7 of them, possibly more, depending on how you count faint extensions. They radiated from the nucleus in multiple directions. Some stretched away from the sun, the classic comet tail configuration. But others pointed sunward, or at angles perpendicular to the sun-comet line, creating a network that looked almost deliberate. Raymond and Prosperi independently confirmed the same structure. Same jets, same geometry, real. The images spread through astronomical communities within hours. Twitter lit up, astronomy forums buzzed. And by November 9th, Michael Buchner and Frank Niebling in the United Kingdom had captured even more dramatic views, using different processing techniques designed to emphasize the faintest structures. Their composite image revealed the full scale of what was happening. The sunward jet extended approximately 950,000 kilometers. The anti-solar tail stretched 2.85 million kilometers in the opposite direction. Together, these structures spanned nearly 3.8 million kilometers, a distance 10 times greater than the Earth-Moon separation. Avi Loeb received the images and immediately began calculations. How much mass does it take to create jets this size? How fast must the material be moving? What forces are required to maintain coherent structure across such distances while fighting solar wind and radiation pressure? The answers were troubling. The jets required enormous mass loss, far more than typical cometary activity produces. The sunward jets required densities 1,000,000 times greater than the solar wind to remain visible against the surrounding plasma. This was not gentle outgassing. This was explosive, sustained, directed ejection on scales that suggested the object was tearing itself apart. Loeb published his analysis online, writing, "Given that a large number of jets appear in many directions, the reported non-gravitational acceleration of 3IATLAS requires much more than 10–20% of its initial mass to have been ejected near perihelion. 10 to 20% is conservative." Other calculations suggested the fraction might be higher, perhaps 30 or even 40% if the ejection is highly directional and asymmetric. What does it mean when a comet loses that much mass? For natural objects, it means catastrophic disintegration is likely. The nucleus is coming apart, fractured by thermal stress, tidal forces, or rapid rotation. But fragmentation produces debris clouds, not structured jets. Fragments spread out randomly, creating diffuse halos and fading tails as smaller pieces evaporate quickly. 3IATLAS showed no such diffusion. The jets were sharp, collimated, persistent across multiple nights of observation as the comet continued moving away from the sun and solar heating began to decrease. By November 10th, additional observations from Italy's Virtual Telescope project added to the dataset. Gianluca Marsi captured images showing a clear ion tail, glowing blue-green from ionized carbon monoxide and water vapor fluorescing under solar ultraviolet light. The tail stretched at least 0.7 degrees, visible even with the comet low on the horizon and a bright moon competing for contrast. The anti-tail was also prominent, pointing toward the east-southeast, creating the classic dual-tail appearance that confuses casual observers. Ground-based spectrographs began capturing detailed spectra of the jets themselves, not just the overall coma. Early results confirmed that the material is mostly carbon dioxide and dust, consistent with what Webb had detected in August. No exotic molecules, no unusual isotope ratios, nothing that screamed artificial. The composition looked cometary. But composition is not the same as behavior. Water and carbon dioxide ejected from a natural ice deposit should create jets that follow predictable trajectories, shaped by gravity, radiation pressure, and gas dynamics. The jets from 3IATLAS followed trajectories that made sense only if something was controlling the flow, or if the geometry of the nucleus and the distribution of ice deposits happened to align in extraordinarily specific ways. The Hubble Space Telescope joined the campaign on November 11th, conducting ultraviolet spectroscopy to measure the sulfur-to-oxygen ratio in the outgassing material. Sulfur compounds are traces of deep interior composition, materials that formed in the protoplanetary disk around the comet's birth star billions of years ago. Measuring those ratios and comparing them to solar system comets could reveal whether 3IATLAS formed in a chemically similar or radically different environment. Results are still being analysed, but preliminary data suggest the sulfur to oxygen ratio is within the range seen in solar system comets. Nothing extraordinary. This is both reassuring and frustrating. Reassuring because it confirms the object is made of natural materials, not exotic alloys or metamaterials we cannot explain. Frustrating because it does not resolve the mystery of the jet geometry. You can build a probe out of ice and rock. You can use cometary material as propellant, heating it and expelling it for thrust. The composition alone does not tell you whether what you are looking at is natural or engineered. By mid-November, the comet was fading as it moved farther from the Sun and Earth. Magnitude 9.9 as of November 11th. Still bright enough for amateur telescopes, but dropping steadily. The observing window was closing. In a few more weeks, it would be too faint for detailed spectroscopy, too distant for high-resolution imaging. The chance to study 3IATLAS at peak activity was already passing. If we wanted answers, we needed to act fast, and the clock was ticking. You need to understand why sunward jets are wrong. Not just unusual, but wrong according to basic physics. When a comet approaches the Sun, two primary forces act on particles ejected from its surface. Gravity pulls them toward the Sun, but gravity is weak at the distances we are talking about. Radiation pressure pushes them away from the Sun as photons from sunlight strike dust grains and transfer momentum. For particles smaller than a few micrometers, radiation pressure overwhelms gravity, and they accelerate anti-sunward, blown into the classic comet tail. For larger particles, millimeter-sized grains, radiation pressure is weaker, and the particles move more slowly, sometimes lagging behind the nucleus in its orbit. Solar wind adds another force. The Sun constantly sheds particles, mostly protons and electrons, streaming outward at 400 kilometers per second. This plasma carries embedded magnetic fields that interact with charged dust grains and ionized gas. The interaction is complex, involving magnetic draping, electric fields, and plasma instabilities. But the net effect is always outward. Solar wind pushes material away from the Sun, always. This is fundamental. This is why comet tails point away. So how do you create a jet pointing toward the Sun? There are three possibilities. First, projection effects. The jet is actually pointing away from the Sun, but viewed from Earth at a specific angle, it appears to point sunward due to foreshortening. This is the explanation for classic anti-tails, structures created when large dust grains lag behind the comet in its orbit and align with our line of sight. When Earth crosses the plane of the comet's orbit, the trailing dust can appear to extend sunward, even though the particles are actually behind the nucleus. Second, magnetic deflection. Charged particles interacting with draped magnetic field lines from the solar wind can be deflected perpendicular to both the field and their velocity. Under very specific field geometries, this deflection can send particles sunward, even though they were initially ejected in a different direction. This mechanism was recently confirmed by NASA's Parker Solar Probe, which measured magnetic draping and electric fields near the Sun, strong enough to accelerate dust grains in unexpected directions. Third, thrust. Something is actively expelling material sunward, using it as reaction mass to decelerate the object. This is how rockets work. Eject mass in one direction, and you accelerate in the opposite direction. If 3IATLAS is a probe entering the solar system at high velocity, it would need to brake to adjust its trajectory. Pointing thrusters sunward and expelling propellant would create exactly what we see, jets streaming toward the Sun while the object slows down. Let us examine each possibility. Projection effects require that we are viewing 3IATLAS at a very specific angle, nearly edge-on to the plane in which dust particles trail behind the nucleus. The November 8th observation geometry had the comet at 29 degrees solar elongation, relatively close to the Sun in Earth's sky. This is not the ideal geometry for anti-tail projection, which works best when Earth is near the orbital plane and the comet is farther from the Sun. But it is not impossible. Careful modeling of the dust dynamics, calculating where particles should be based on ejection velocity and radiation pressure, could determine whether projection explains what we see. That modeling has not been published yet. The data exist, the orbital elements are known, the observing geometry is recorded. Someone needs to sit down and run the simulations, tracing particle trajectories and comparing predicted positions to observed structure. If the model matches, projection is confirmed. If it does not, projection is ruled out. Magnetic deflection is harder to test because it requires knowing the local solar wind conditions when the jets were observed. Parker's solar probe provides measurements, but it is not at the same location as 3IATLAS, and solar wind is highly variable, changing on timescales of minutes as magnetic structures flow past. Reconstructing the field geometry at the comet's location requires models that extrapolate Parker's data and account for solar rotation, coronal mass ejections, and other transient events. These models are sophisticated but uncertain. You can make predictions, but confirming them requires in situ measurements, spacecraft actually at the comet taking data. We do not have that. Thrust is the simplest explanation mechanically. If the jets are real, if they are genuinely pointing sunward and not optical illusions, then something is expelling material in that direction. Natural sublimation does not do this. Sublimating ice ejects gas radially outward from the surface, driven by vapor pressure. The gas drags dust grains along, creating jets that follow ballistic trajectories shaped by gravity and radiation. Those trajectories never point sunward unless you invoke special conditions like crater geometry, focusing the flow, or subsurface reservoirs, channeling gas through vents, oriented in specific directions. Could the nucleus have a crater or depression that focuses outgassing sunward? Possibly. Comet Tempel 1, observed by NASA's Deep Impact mission in 2005, had active regions inside craters where sublimation was concentrated. Comet Hartley 2, visited by the EPOCHI mission in 2010, showed jets emanating from rough, irregular terrain where volatile ices were exposed. If 3IATLAS has a large crater facing the Sun, gas sublimating from the crater floor could be funneled sunward by the surrounding walls. But this explanation requires a very specific nucleus shape, a crater of the right size and depth, oriented just so. It also does not easily explain why there are multiple sunward jets, unless the nucleus has multiple craters, all facing the Sun simultaneously, which strains credibility. You are adding assumptions, tuning parameters to fit observations. The more tuning required, the less confident you can be that the model reflects reality. The key test is trajectory analysis. If the sunward jets represent real thrust, the comet should show non-gravitational acceleration, a deviation from the orbit predicted by gravity alone. Early observations of 3IATLAS, before perihelion, already detected such acceleration, small but measurable, requiring adjustment to the orbital elements to match observed positions. This is the same signature one Oumuamua showed, the anomaly that sparked years of debate about whether it was a comet outgassing invisibly or something else. If the non-gravitational acceleration vector aligns with the sunward jets, if the direction of the observed thrust matches the direction the jets are pointing, then you have strong evidence that the jets are producing the acceleration. This is not proof of artificial propulsion. Natural outgassing can produce non-gravitational acceleration, but it ties the visible activity to the orbital anomaly in a way that demands explanation. No one has published that analysis yet. The astrometry, the precise positional measurements needed to calculate acceleration vectors, is still being collected. Observers are tracking 3IATLAS night after night, measuring its position relative to background stars, building the dataset needed for orbital refinement. In weeks or months, someone will calculate the acceleration, determine its magnitude and direction, and compare it to the jet geometry. That comparison might resolve the question, or it might just deepen the mystery. Let us confront it directly. What if 3IATLAS is not a comet? What if the jets are not random sublimation but controlled thrust from an object designed, built, and launched by intelligence that arose around another star billions of years ago? What if we are watching a spacecraft execute a maneuver? This is not science fiction. This is hypothesis testing. You observe something unusual, you propose explanations, you test them against data. The artificial hypothesis is testable, falsifiable, and consistent with known physics. It is also deeply uncomfortable because accepting it means accepting that we are being visited, that someone else exists, that we are not alone and never were. Start with the basics. If you want to send a probe to another star system, you face extraordinary challenges. The distances are vast. Alpha Centauri, the nearest star system, is 4.3 light-years away, roughly 40 trillion kilometers. At the speeds our fastest spacecraft achieve, Voyager, one traveling at 17 kilometers per second relative to the Sun, the journey would take 75,000 years. Any civilization sending probes across such distances either has propulsion far beyond ours or accepts that the missions will last millennia, far longer than civilizations typically endure. If you accept the long timescale, you design for autonomy and resilience. The probe cannot rely on real-time control. Radio signals take years to cross interstellar distances. By the time a command reaches the probe and a response returns, conditions have changed. The probe must navigate, diagnose failures, make decisions on its own. You build in massive redundancy, radiation-hardened systems, self-repair capabilities if possible. You power it with something long-lived, isotopes with half-lives of millions of years, or energy sources we have not invented yet. You also design for efficiency. Carrying all your propellant from the start is prohibitively massive. Instead, you refuel in flight. Scoop material from the interstellar medium, hydrogen and helium, drifting between stars, or design the probe to use whatever it encounters at the destination. If you arrive at a solar system and find icy bodies, comets, asteroids, moons, you harvest material and use it as reaction mass, heat it, expel it, generate thrust. This is called in situ resource utilization, and it is central to every serious interstellar mission concept we have studied. Now imagine 3IATLAS in that context. It enters the solar system from interstellar space, moving at 35 kilometers per second, far too fast to be captured into orbit by the Sun's gravity. If the mission requires slowing down, gathering data, perhaps eventually achieving orbit or flyby of specific targets like Earth or Jupiter, the probe must brake. The most efficient place to brake is near perihelion, closest approach to the Sun, where gravitational potential energy is highest, and a small velocity change produces the largest effect on the trajectory. This is called an O-berth maneuver, exploiting the gravity well to amplify thrust efficiency. To brake, you need to expel mass opposite your direction of motion. If you are moving sunward at perihelion, you fire thrusters sunward, creating jets pointing toward the Sun. You use the comet itself as propellant, heating ice deposits on the surface or interior, sublimating them explosively, and channeling the vapor through nozzles arranged around the hull. 7 nozzles provide redundant control. Fire them symmetrically for pure braking. Fire subsets in combinations to adjust attitude and orientation without complex gimbals. The jets would look exactly like what we see in the November 8th and 9th images. Multiple streams, some sunward, some at angles, densities high enough to remain visible against solar wind, persistence across days or weeks as the maneuver continues. The mass loss, 10 to 30% of total mass, makes sense if the probe is designed as a single-use system, expendable, built to complete one mission and then degrade or shut down. Using 30% of your mass as propellant is aggressive, but not absurd if you knew before launch that refueling opportunities would exist at the destination. This explains the carbon dioxide dominance. Carbon dioxide sublimes at lower temperatures than water, making it easier to vaporize with less energy input. If you are designing a probe to use cometary material as propellant, you would preferentially target carbon dioxide-rich regions because they are easier to process. The high carbon dioxide to water ratio in 3IATLAS is not a mystery in this scenario, it is a design choice. It explains the non-gravitational acceleration. The probe is maneuvering, so of course it deviates from a purely gravitational trajectory. The acceleration is not random. It is directed, correlating with the jets, exactly what you would expect from thruster operation. It even explains the symmetry. 7 jets arranged in a network is improbable for random ice deposits, but expected for engineered thruster placement. You want coverage around the hull, ability to fire in multiple directions, redundancy in case nozzles fail during the millions of years between launch and arrival. But this hypothesis has problems. We have detected no radio signals from 3IATLAS. Multiple radio telescopes have listened, searching for narrow-band emissions or modulated signals that might indicate communication or operational systems. Nothing. Silence. You could argue the probe uses frequencies we do not monitor, or communication protocols we do not recognize, or that it is deliberately silent, designed to observe without revealing itself. But each argument adds assumptions. The spectroscopy shows natural cometary composition: carbon dioxide, water, dust, organic compounds. Nothing exotic, no metals or synthetic materials we can detect. You could argue the probe is camouflaged, covered in cometary material harvested during transit, or built into its structure from the start, designed to look natural. But again, you are adding layers of explanation. The jets themselves, when analysed in detail, show velocities and particle sizes consistent with natural sublimation, not high-efficiency propulsion. Gas moving at a few hundred meters per second, dust grains averaging 0.1 millimeters, typical for comets. If you were using ion drives or nuclear thermal propulsion, exhaust velocities would be much higher, thousands or tens of thousands of meters per second. The fact that we see slow-moving particles suggests either natural outgassing or extremely inefficient propulsion deliberately tuned to mimic natural behavior. The artificial hypothesis also requires accepting that interstellar probes exist and pass through our solar system with some frequency. We have found 3 interstellar objects in 8 years. If probes are common, we should find many more as our surveys improve. If they are rare, finding one in such a short observation baseline is extraordinarily lucky, or suggests they are not rare at all, just undetected until recently. This is where the Vera Rubin Observatory becomes critical. When it begins full operations in 2026, Rubin will survey the sky every few nights with unprecedented sensitivity. It will detect interstellar objects months or years before they reach perihelion, giving us time to plan missions, request telescope time, and study them in detail. If we start finding dozens of interstellar visitors, and most look normal, while 1 or 2 show anomalies, like 3IATLAS, the statistics will guide us. If every interstellar object shows structured jets and unusual activity, then either our models of cometary behavior are deeply flawed, or we are being visited regularly and only now noticing. Avi Loeb has called for targeted observations using the most powerful telescopes available. Point the Hubble Space Telescope at 3IATLAS, resolve the nucleus, look for surface structure that does not match natural fragmentation. Use the James Webb Space Telescope for high-resolution spectroscopy of individual jets. Search for compositional differences that might indicate engineered materials or controlled release. Task radio telescopes to conduct deep searches across broad frequency ranges. Listen for any signal, however faint or unusual. Loeb argues that the stakes are too high to dismiss the artificial hypothesis without thorough investigation. If 3IATLAS is natural, we learn about interstellar comets and expand our understanding of planetary system formation. Important science, but incremental. If 3IATLAS is artificial, even if it is inactive, derelict, a million-year-old probe that has long since failed, the discovery would be transformative. Proof of extraterrestrial intelligence, confirmation that technological civilizations exist and build things and send them across the galaxy. This would be the most significant finding in human history, altering our understanding of our place in the cosmos, our future, our responsibility to ourselves, and whatever others might be out there. The scientific community is divided. Most astronomers favor natural explanations, arguing that we should exhaust all conventional possibilities before invoking extraordinary ones. Comets are diverse, surprising, capable of behavior we have not seen before because our observational baseline is limited. 3IATLAS might be unusual but still natural, an outlier on the extreme end of variation. Others, a smaller but vocal group, argue that the anomalies are too many, too structured, too persistent to dismiss. They call for taking the artificial hypothesis seriously, devoting resources to testing it rigorously rather than assuming it away. This is how science works. You argue, you test, you gather data, but the data must be gathered soon. 3IATLAS is fading, moving away from the sun at high speed, leaving the solar system forever. By December 19th, 2025, it will reach its closest approach to Earth, still 1.8 astronomical units away, 269 million kilometers, far beyond any chance of sending a spacecraft to intercept. That is our last opportunity for the best observing geometry. After that, the comet recedes, fading into the darkness beyond Neptune, undetectable by anything we have built. If we wait too long, If we argue about methodology and funding and telescope access while the window closes, we lose the chance to know, and that might be the tragedy. Not that we looked and found nothing, but that we did not look hard enough because we were afraid of seeming foolish, or because we convinced ourselves the answer had to be mundane. 3I.ATLAS is not the first interstellar object we have found, and understanding the others provides critical context for interpreting what we see now. Each visitor has been different, each has challenged our expectations, and together they are teaching us that interstellar space contains far more diversity than our solar system examples suggest. 1I, Oumuamua, arrived first, discovered on October 19, 2017, by the Pan-STARRS telescope in Hawaii. The name means scout or messenger in Hawaiian, chosen because this was humanity's first confirmed visitor from beyond. Oumuamua was strange from the beginning. Long and thin, with an aspect ratio of roughly 10:1, it looked like a cigar or a needle tumbling end over end through space. Its light curve, the way its brightness varied as it rotated, suggested extreme elongation unlike any asteroid or comet we had seen. But the strangest part was its motion. As Oumuamua left the solar system, accelerating away from the sun, it moved slightly faster than gravity alone predicted. The deviation was small but measurable, requiring adjustment to the calculated orbit. Comets show this behavior routinely. Outgassing produces thrust, pushing them off purely gravitational trajectories. But Oumuamua showed no visible coma, no tail, no sign of activity. Sensitive observations with Spitzer Space Telescope and other infrared instruments searched for dust and gas. Nothing detected. If there was no outgassing, what caused the acceleration? Some scientists proposed that Oumuamua was venting gas we could not detect, perhaps hydrogen or nitrogen, invisible in optical and infrared wavelengths. Others suggested it was a fractal aggregate, a fluffy structure with high surface area that experienced strong radiation pressure. Avi Loeb proposed something more provocative. Oumuamua might be a light sail, a thin sheet designed to catch starlight and convert it to motion, technology from another civilization. The debate raged for months. Papers were published arguing both sides. Data were reanalyzed, models refined, but Oumuamua faded and vanished before consensus emerged, carrying its secrets into the void. We never determined definitively whether it was natural or artificial, though the majority opinion leans toward natural, with unusual properties we do not fully understand. 2 years later, in August 2019, 2I, Borisov arrived. Discovered by amateur astronomer Gennady Borisov using a telescope he built himself, this object behaved exactly as we expected comets to behave. It had a classic tail streaming away from the sun. It showed a dusty coma. Spectroscopy revealed water vapor, carbon monoxide, cyanide, all the usual cometary molecules. It looked like solar system comets, confirming that comet formation is probably universal, that icy bodies condensing in protoplanetary disks around other stars resemble those around our sun. Borisov was almost boring in its normality, and that was comforting. It suggested that most interstellar objects would be unremarkable, scientifically interesting but not paradigm-shattering. We could study them with existing tools and models, expanding our database without confronting uncomfortable questions about artificial origins. And then came 3I.ATLAS. Discovered in July 2025, it initially seemed to follow Borisov's template. A comet, outgassing normally, developing a tail, brightening as it approached the sun. Early spectroscopy found carbon dioxide and water, expected molecules. The community relaxed. Another boring interstellar comet, valuable for comparative studies but not revolutionary. Perihelion changed everything. The eruption, the massive mass loss, the structured jets pointing in impossible directions. Suddenly, 3I.ATLAS was not boring. It was the most perplexing object we had encountered, combining Oumuamua's anomalous acceleration with visible activity that raised more questions than it answered. 3 objects, 3 radically different presentations. Oumuamua, inactive and accelerating mysteriously. Borisov, entirely normal and reassuring. 3I.ATLAS, hyperactive and defying simple explanation. What does this tell us? Statistically, almost nothing. A sample size of 3 is far too small to draw conclusions about the underlying population. Are most interstellar visitors like Borisov and Oumuamua and 3I/ATLAS are outliers? Or is there no typical interstellar object, just enormous diversity reflecting the variety of stellar environments where these bodies form? We cannot answer that yet. But we can say that interstellar space is not uniform. Objects arriving from other star systems carry the chemical signatures of their birth environments, regions with different temperatures, different elemental abundances, different radiation fields. Some form in cold outer disks, where carbon dioxide and nitrogen dominate. Others form closer to their stars, where water ice is more common. Some are ancient, billions of years old, ejected during the chaotic early phases of planetary system formation. Others are young, recently expelled during late-stage gravitational interactions. The diversity we see in 3 objects hints that many more categories exist, waiting to be discovered. When Rubin comes online and begins finding interstellar visitors routinely, we will build statistics, identify patterns, classify objects into families based on composition and activity. 3I/ATLAS will either fit into a known category, unusual but explicable, or it will remain an outlier, forcing us to create a new category that might include only one member. The other lesson from Oumuamua and Borisov is that initial impressions can be misleading. Oumuamua looked inactive and safe to interpret until someone noticed the acceleration and everything became uncertain. 3I/ATLAS looked normal until perihelion, when it erupted. We are learning not to assume, not to relax into comfortable explanations too quickly. Every new data point can overturn the model. This is both the frustration and the excitement of studying interstellar objects. We get one pass, one brief observing window, and then they are gone forever. We cannot wait for them to return like periodic comets. We cannot send missions years in advance to intercept them because we do not know they exist until they are already inbound. We scramble, request telescope time, coordinate observers worldwide, and hope we capture enough data before the window closes. For 3I/ATLAS, that window is closing fast. The comet is already magnitude 9.9 and fading. Within weeks, it will be too faint for detailed spectroscopy. Within months, only the largest telescopes will track it. By mid-2026, it will be gone, another dim speck lost in the background of distant stars. If we have not gathered the data we need by then, we never will. This is the reality of interstellar object science. Opportunity is fleeting, mistakes are permanent. December 19th, 2025 will mark a singular moment in human history. On that date, 3I/ATLAS will reach its closest point to Earth, passing 1.8 astronomical units away, roughly 269 million kilometers. That is twice the distance to Mars at opposition, far beyond any hope of physical contact, but close enough for our most powerful telescopes to capture the best possible data before the comet recedes forever into interstellar darkness. This is our last window, our final opportunity to gather evidence that might resolve whether we are looking at nature's complexity or something designed. The geometry on December 19th places 3I/ATLAS high in the morning sky for Northern Hemisphere observers, located near Regulus, the brightest star in Leo. The comet will still be faint, magnitude 11 or 12, requiring telescopes with at least 6-inch apertures and long exposure imaging to detect. But for professional observatories, this represents optimal conditions. The comet will be rising around 11 p.m. local time, giving observers all night to accumulate data before dawn interferes. Multiple facilities are already planning observation campaigns. The Virtual Telescope project in Italy will host a live stream, allowing the public to watch in real time as automated telescopes track the comet across the starfield. Gianluca Massi, who has been documenting 3I/ATLAS since early November, will combine dozens of exposures to reveal the tail structure and any changes in jet activity since perihelion. Amateur astronomy networks worldwide will coordinate simultaneous observations, creating a distributed array that captures the comet from multiple angles and improves the signal-to-noise ratio through statistical combination. But the critical observations will happen at wavelengths invisible to human eyes. Radio telescopes will conduct deep searches for narrowband emissions, signals that might indicate electronic systems operating inside the nucleus. X-ray observatories will look for fluorescence from solar-wind interactions, mapping the magnetic environment around the comet to test whether field deflection can explain the sunward jets. Infrared telescopes will measure thermal emission, determining whether the nucleus temperature distribution matches natural solar heating or shows hotspots that might indicate internal heat sources. The Hubble Space Telescope has already completed its ultraviolet spectroscopy campaign in mid-November, measuring the sulfur-to-oxygen ratio and other compositional tracers. Results are still being analysed, but preliminary data show nothing extraordinary, reinforcing the natural composition narrative. The James Webb Space Telescope is scheduled for additional observations in late November and early December, targeting individual jets with high-resolution near-infrared spectroscopy to search for compositional differences that would prove they originate from separate subsurface reservoirs. Ground-based adaptive optics systems at observatories like the Keck telescopes in Hawaii and the Very Large Telescope in Chile will attempt to resolve the nucleus itself, imaging it as more than a point source, mapping its shape and surface features. If the nucleus is irregular, fractured, showing impact craters or rough terrain that supports the natural interpretation. If it is smooth, symmetrical, showing geometric patterns or surface structure inconsistent with random accretion, that would be extraordinary and demand explanation. Astrometry continues to be crucial. Observers are measuring the comet's position relative to background stars with subarc-second precision, building the dataset needed to calculate non-gravitational acceleration vectors. By December, enough measurements will exist to determine whether the acceleration aligns with the visible jets, whether the magnitude matches what the observed mass loss predicts, and whether the direction is consistent with random outgassing or deliberate maneuvering. If the acceleration vector points sunward and matches the orientation of the sunward jets, that ties the visible activity directly to the orbital anomaly. It does not prove artificial propulsion, but it strengthens the case that something unusual is happening, something beyond the standard model of cometary sublimation. If the acceleration is perpendicular to the jets, or if its magnitude is much larger or smaller than the mass loss can explain, that suggests we are missing something. Perhaps internal fragmentation creating momentum transfer we cannot see. Perhaps outgassing from nightside vents hidden from Earth's view. Perhaps radiation pressure on an asymmetrically shaped nucleus, creating torque that changes the spin state and generates non-gravitational forces through complex dynamics. The challenge is that 3IATLAS is fading. By mid-November, it had already dropped to magnitude 9.9, and the trend is accelerating as the comet moves farther from the Sun and solar heating decreases. Activity is declining. The jets that were so prominent in early November, images are weakening, becoming harder to detect against background noise. By December 19th, the comet might show only a faint tail and a dim coma, the spectacular multi-jet structure reduced to memory and archived images. This is the cruel reality of interstellar object astronomy. You get one chance, the object arrives, brightens, passes perihelion, and fades, all within a span of months. There is no second opportunity to capture that missing spectrum or resolve that critical detail. If your telescope had bad weather during the key observing window, if your proposal for telescope time was rejected, if you did not realize the importance of the observation until it was too late, the data gap remains forever. Oumuamua taught us this lesson harshly. By the time the astronomical community recognized how anomalous it was, the object had already passed perihelion and was receding rapidly. Telescopes struggled to track it, and within weeks, it was too faint for all but the largest instruments. Critical observations that might have resolved the outgassing question or imaged the surface in detail were never conducted because no one anticipated the need until the opportunity had passed. We are trying not to repeat that mistake with 3IATLAS. The anomalies are recognized, the observation campaigns are planned, resources are being allocated. But coordination is difficult, priorities, conflict, and telescope time is finite. Every hour spent on 3IATLAS is an hour not spent on other science, other targets competing for attention. Committees weigh the requests, assess the scientific merit, and sometimes conclude that the uncertainty is too high, the chance of definitive results too low to justify the cost. This is where Avi Loeb's advocacy becomes critical. By publicly arguing that 3IATLAS deserves serious investigation, that the artificial hypothesis must be tested rigorously, He applies pressure that committees cannot ignore. Media attention follows, public interest builds, and suddenly, the political cost of not observing becomes higher than the scientific risk of allocating resources to what might turn out to be a wild goose chase. Science does not happen in a vacuum. It is a human endeavor, shaped by personalities, funding, politics, and the willingness of individuals to stake their reputations on controversial ideas. Loeb has been willing to do that, and whether he is ultimately proven right or wrong about interstellar artifacts, his willingness to ask uncomfortable questions has forced the community to take 3IATLAS seriously in ways it might not have otherwise. By December 20th, the opportunity will be passing. Earth will be moving away from the comet's trajectory, increasing the distance and worsening the observing geometry. The comet will sink lower in the morning sky, setting earlier, giving observers fewer hours per night to collect data. By Christmas, it will be magnitude 12 or fainter, detectable only with substantial effort. By February 2026, it will be beyond Neptune's orbit, invisible to all but the most sensitive surveys. And then it will be gone, leaving the solar system at 35 kilometers per second, carrying its secrets back into the interstellar void. The data we have collected by then will be all we ever have. The questions we did not ask, the observations we did not conduct, will haunt us as the comet fades into the catalogue of what might have been. This is why December 19th matters. This is why astronomers are preparing, coordinating, and lobbying for telescope time. Because this is the end, the final act, the last chance to know. While 3IATLAS was hidden from Earth during solar conjunction in early October, two spacecraft orbiting Mars had a front row seat. ESA's Mars Express and the ExoMars Trace Gas Orbiter turned their cameras toward the interstellar visitor as it passed within 30 million kilometers of the red planet on October 3, 2025. These observations, conducted weeks before the spectacular post-perihelion jets appeared, might hold clues we are only beginning to understand. The Mars orbiters were not designed for deep space imaging. Their cameras are optimized for photographing the Martian surface from altitudes of a few hundred to a few thousand kilometers, capturing details of canyons, craters, and polar ice caps. Pointing those same cameras at a dim comet 30 million kilometers away is like using a microscope to photograph a mountain. The optics are not matched to the task, and success was far from guaranteed. ExoMars Trace Gas Orbiter used its Cassis camera, the color and stereo surface imaging system, capturing a series of exposures with 5-second integration times. The resulting images show 3IATLAS as a slightly fuzzy white dot moving against the starfield, clearly visible but not resolved. The nucleus, probably only a few kilometers across, was far too small to distinguish from the surrounding coma. Imaging a kilometer-sized object at 30 million kilometers is equivalent to seeing a mobile phone on the moon from Earth. Impossible without apertures and resolutions these spacecraft do not possess. But the coma itself, thousands of kilometers across, appears clearly. ESA scientists created animations by combining multiple frames, showing the comet moving downward through the field of view, trailing a faint haze of gas and dust. The coma's size, brightness, and structure provide information about activity levels at that time, roughly 4 weeks before perihelion, when solar heating was ramping up but had not yet reached maximum intensity. Nick Thomas, principal investigator for the Cassis camera, described the challenge. This was a very challenging observation for the instrument. The comet is around 10,000 to 100,000 times fainter than our usual target. Detecting something that faint required pushing the camera to its limits, maximizing exposure time, while keeping the spacecraft pointed accurately enough that the comet did not drift out of the frame during the integration. Mars Express attempted similar observations using its visual monitoring camera, but with exposure times limited to just 0.5 seconds, the comet has not yet clearly appeared in the data. Scientists are combining multiple frames, stacking them to improve signal to noise, searching for the faint signature buried in the noise. The work continues, and results might emerge in coming weeks. Why do these October observations matter? Because they capture 3IATLAS in a different state, before the eruption. If the jets that appeared in early November were triggered by perihelion heating, then the October images should show lower activity, a more quiescent coma, possibly no visible jets at all. If the jets were already present in October, that suggests they are not purely a perihelion phenomenon, but a sustained feature of the object's behavior. Preliminary analysis suggests the October coma was relatively symmetric and diffuse, without obvious directional structures. This supports the interpretation that the November jets represent increased activity triggered by perihelion heating. But detailed comparison requires careful processing, photometric calibration, and modeling to account for different viewing geometries and instrument sensitivities. ESA's Jupiter Icy Moons Explorer, JUICE, also observed 3IATLAS in early November, shortly after the spacecraft completed a gravitational slingshot maneuver around Earth. JUICE's instruments are designed for studying Jupiter's moons, Ganymede, Callisto, and Europa, when it arrives in 2031, but they are capable of observing comets if opportunities arise. The spacecraft was farther from 3IATLAS than the Mars orbiters, but it captured the comet in a more active state, just after perihelion, potentially revealing details the Earth-based observations missed. Data from JUICE will not be downlinked until February 2026. The spacecraft is currently far from Earth and bandwidth is limited, so science data is stored on board and transmitted during scheduled communication windows months later. This delay is frustrating but unavoidable. When the data arrives, it will provide an independent dataset from a completely different viewing angle, allowing triangulation and 3D reconstruction of the jet structures. The Mars and JUICE observations highlight a broader point. We need more spacecraft in the right places at the right times. Interstellar objects arrive unpredictably, and ground-based telescopes have limitations imposed by weather, daylight, and solar conjunction. Space-based assets, distributed throughout the solar system, can observe continuously from multiple angles, capturing data Earth-based observers cannot access. This is the motivation behind ESA's Comet Interceptor mission, scheduled to launch in 2029. Unlike traditional missions that target a specific comet known years in advance, Comet Interceptor will launch into a parking orbit at the L2 Lagrange point and wait. When a suitable target appears, either a pristine long-period comet from the Oort cloud, or, ideally, an interstellar visitor like 3IATLAS, the spacecraft will leave its parking orbit and execute a high-speed flyby, capturing close-range images and spectra as it passes. If Comet Interceptor had been operational in 2025, it could have targeted 3IATLAS, potentially intercepting the comet during or shortly after perihelion when activity was peaking. A flyby at a few thousand kilometers would resolve the nucleus surface in stunning detail, reveal the source regions of the jets, measure composition in situ, and answer definitively whether we are looking at natural outgassing or something else. The mission is not operational yet, and 3IATLAS will be long gone before Comet Interceptor reaches its parking orbit. But the concept proves we are learning from missed opportunities, adapting our strategies, building infrastructure to study future visitors more effectively. In the meantime, the Mars observations provide a valuable baseline. They show what 3IATLAS looked like before perihelion, establishing a reference state against which post-perihelion changes can be measured. They demonstrate that the comet was already active in early October, outgassing significantly, even at 1.5 astronomical units from the Sun, consistent with the high carbon dioxide content detected by Webb. And they remind us that sometimes the most important data comes from unexpected sources. Mars Express and ExoMars were not designed for this. No one planned these observations when the missions launched. But scientists recognized an opportunity, repurposed instruments, took the risk of attempting difficult observations with uncertain payoff, and succeeded in capturing data that will contribute to solving the mystery. This is science at its best: adaptive, creative, seizing opportunities as they arise, and willing to push instruments beyond their original design limits in pursuit of knowledge. The Mars observations are a small piece of the 3IATLAS puzzle, but every piece matters when you are trying to understand something entirely new. Gravity is clean, predictable. When you know the masses and distances involved, you can calculate trajectories with exquisite precision, predicting where an object will be years in advance. This is how we send spacecraft to Mars, how we navigate the solar system, how we find asteroids decades before they might threaten Earth. The mathematics is well established, tested across centuries of observations, and it works. Until it doesn't. Non-gravitational acceleration is what astronomers call the tiny deviations, the small forces beyond gravity that push objects off their predicted paths. For comets, the primary source is outgassing. As ice sublimates, gas molecules leave the surface carrying momentum. Each departing molecule pushes back against the nucleus, creating thrust. Sum those pushes over billions of molecules per second, and you get measurable acceleration. The effect is small but detectable. For a typical comet, non-gravitational acceleration might be a few millionths of a meter per second squared, enough to shift the comet's position by hundreds or thousands of kilometers over weeks or months. Astrometry, precise measurement of the comet's position relative to background stars, reveals these shifts. You compare observed positions to predicted positions calculated from gravity alone, and the difference tells you something is accelerating the object. 3IATLAS showed non-gravitational acceleration from the beginning. Early orbital calculations based on observations in July and August 2025 required adjustment to match positions measured in September. The comet was not where gravity alone predicted. Something was pushing it. This was not surprising. The comet was outgassing visibly, showing a coma and tail, so some thrust was expected. But determining the magnitude and direction of that thrust, and confirming it matches the observed activity, requires careful analysis. You need many precise positional measurements spread over weeks, accounting for Earth's motion, correcting for atmospheric refraction, removing systematic errors introduced by telescope optics and detector calibration. The Jet Propulsion Laboratory, which tracks all solar system objects and calculates their orbits, incorporated non-gravitational terms into the 3IATLAS orbit solution as more data accumulated. These terms, typically labeled A1, A2, and A3 in the equations of motion, represent radial, transverse, and normal components of acceleration. A1 points along the Sun-comet line, A2 points perpendicular in the direction of the comet's motion, A3 points perpendicular to the orbital plane. For most comets, A1 dominates because outgassing is strongest on the sunlit side and produces mainly radial thrust. A2 is usually smaller but non-zero because the nucleus rotation causes gas to jet slightly off-radial as the surface rotates. A3 is typically tiny, close to measurement noise, unless the spin axis is tilted significantly relative to the orbital plane. The preliminary values for 3IATLAS, calculated before perihelion when data were still sparse, suggested significant A1 and A2 terms. This indicated the comet was accelerating both radially and transversely, consistent with active sublimation from a rotating nucleus. But the exact values were uncertain, carrying large error bars because the comet was faint and positional measurements had scatter. Post-perihelion observations are critical for refining these values. As the comet brightened and activity increased, positional measurements became more precise. Observers worldwide submitted astrometry to the Minor Planet Center, which aggregates data and distributes it to orbit calculators. By early November, hundreds of measurements existed, spanning July through November, enough to constrain the non-gravitational acceleration with much better precision. The results are still being finalized, but leaked preliminary values suggest the non-gravitational acceleration is larger than typical comets show. Larger even than expected given the observed brightness and dust production rate. This implies either the outgassing is more efficient than normal, converting a higher fraction of sublimated mass into usable thrust, or something about the geometry amplifies the effect. Efficient outgassing happens when gas is channeled through narrow vents, achieving high velocity before expanding into space. Think of it as the difference between a garden hose with no nozzle and one with a nozzle that focuses the stream. The same water flow rate, but the nozzle version produces a tighter, faster jet with more momentum. If 3IATLAS has vents structured to channel sublimating gas efficiently, that could explain higher thrust per unit mass. Geometric amplification happens when jets are directed asymmetrically. If all the outgassing occurred from the sunlit hemisphere and expelled gas radially, much of the momentum would cancel out due to symmetry, producing relatively weak net thrust. But if the jets are concentrated in specific directions, the momentum does not cancel, and you get stronger net acceleration. The November images showing 7 jets in a network configuration suggest asymmetric geometry. If those jets represent the dominant outgassing regions, and if they are oriented to produce sunward thrust, then the non-gravitational acceleration should point sunward, and its magnitude should correlate with the mass loss rate, inferred from jet brightness. This is the test. Calculate the expected thrust from the observed jets, compare it to the measured non-gravitational acceleration, and see if they match. If they do, the mystery is solved within the natural framework. The jets are producing the acceleration, and while the geometry is unusual, it is explicable by subsurface ice distribution and nucleus spin. If they do not match, if the acceleration is too large or points in the wrong direction, then something else is happening. Either there are jets we cannot see, night-side vents ejecting material away from Earth's line of sight, or the acceleration is not coming from sublimation at all. The artificial hypothesis predicts specific values. If 3IATLAS is a probe using its mass as propellant for braking thrust, the acceleration should point roughly sunward, opposing the inbound velocity vector. Its magnitude should be consistent with expelling 10 to 30% of total mass at velocities typical of rocket exhaust, a few hundred to a few thousand meters per second. Comparing the models to data is straightforward in principle. In practice, it is messy because the data are noisy, the models have free parameters, and different teams use different assumptions and computational methods. Papers will be published, disagreements will emerge, and the debate will continue for months or years. But the non-gravitational acceleration is not subjective. It is measurable, quantifiable, and ultimately verifiable by anyone with access to the astrometry data and the computational tools to fit orbits. This makes it one of the most important pieces of evidence, not the images, which can be interpreted multiple ways, not the spectra, which show expected compositions, but the dynamics. The motion of the object through space, shaped by forces we can measure and attribute. Oumuamua's non-gravitational acceleration remains unexplained. Natural models invoking invisible outgassing require fine-tuning and assumptions about composition. The artificial light sail hypothesis fits but requires accepting extraordinary claims. The debate never resolved because the object disappeared before enough data were collected. 3IATLAS offers a second chance, more observations, better instruments, higher activity levels, making the forces larger and easier to measure. If we handle this correctly, if we prioritize the right observations and analyze the data rigorously, we can definitively determine whether non-gravitational acceleration is consistent with natural cometary behavior or demands an alternative explanation. December's astrometry will be critical. By then, the comet will have been observed over a 5-month baseline, providing the temporal leverage needed to measure acceleration accurately. If those measurements come back, showing sunward thrust, matching the jet configuration, the natural model stands. If they show something anomalous, the questions will intensify, and the pressure to conduct follow-up observations before the comet fades will become overwhelming. The invisible force acting on 3IATLAS is the key. We cannot see it directly, but we can measure its effects and trace it back to its source. That detective work, tedious and technical and unglamorous, might be what finally resolves the mystery. Consider the possibility that we are asking the wrong questions. That the dichotomy between natural comets and artificial probe is a false choice, a failure of imagination, shaped by our limited experience. What if 3IATLAS is neither? Interstellar space is vast, and we have sampled almost none of it. 3 objects in 8 years tells us virtually nothing about the population, the diversity, the exotic phenomena that might exist in the gulfs between stars. We are like marine biologists who have seen 3 creatures from the ocean: a jellyfish, a shark, and something strange that does not fit known categories. Declaring that all ocean life must be either jellyfish or sharks would be absurd. Yet that is essentially what we do when we insist interstellar objects must be either natural or artificial, with no intermediate possibilities. What if there are entire categories of objects we have not imagined? Structures formed by processes we do not understand, shaped by environments we have never encountered, behaving according to rules we have not written down. The universe is older and larger than our models, and it has had billions of years to create surprises. Consider the possibility of biotic objects, not spacecraft, but living structures, organisms adapted to the interstellar environment. Science fiction has explored this concept, panspermia taken to its logical extreme, but we dismiss it as fantasy because we have no evidence. But absence of evidence is not evidence of absence when we have barely begun to look. Tardigrades can survive vacuum and radiation. Bacterial spores can remain dormant for millions of years and revive when conditions become favorable. Life on Earth adapted to extremes we once thought impossible. Boiling hydrothermal vents, acidic lakes, frozen Antarctic deserts. Why assume life cannot adapt to space? Why rule out organisms that grow in the tenuous gas and dust between stars, feeding on starlight and cosmic rays, reproducing by budding or fission, drifting for eons until chance brings them to a solar system where they might flourish? A biotic object entering our solar system would show unexpected behavior. It might react to solar radiation in ways that do not match simple sublimation. It might change shape or activity in response to environmental cues. It might have internal structures that regulate outgassing, channels and reservoirs that look designed but evolved naturally through selection pressures we cannot guess at. This is wild speculation, but so is the artificial probe hypothesis. Both require accepting that our experience is incomplete, that the cosmos contains things we have not categorized. The difference is cultural. We can imagine technology from other civilizations because we build technology ourselves. We struggle to imagine alien biology radically different from Earth's because we have only one example of life, and extrapolating from a sample size of one is dangerous. Consider another possibility: post-biological structures. Objects that were once designed and built but have since evolved or degraded beyond recognition. A probe sent by a long-dead civilization, damaged by cosmic rays and micrometeoroid impacts over millions of years, its systems failing, its mission forgotten, now behaving in ways its creators never intended because the control systems have randomized and improvised survival. Or a von Neumann machine, a self-replicating probe that copies itself using materials harvested in each solar system it visits. After thousands or millions of generations, subjected to mutation and selection as copying errors accumulate, the descendants might bear little resemblance to the original design. They would retain core functions, movement, and replication, but the details would drift, creating diversity and unpredictability. This model predicts objects that show hints of both natural and artificial properties, ambiguous signatures that resist clean categorization. Composition mostly natural because they are built from locally sourced cometry and asteroidal material. Behavior partly structured, partly chaotic, because degraded control systems sometimes work and sometimes fail. Non-gravitational acceleration that does not quite fit models because the thrust mechanisms are inconsistent, firing erratically as failing systems struggle to execute ancient programming. 3IATLAS might fit this description. Mostly natural composition, structured jets that seem purposeful but not perfectly controlled, massive mass loss, suggesting inefficiency or damage. A dying probe, executing its final maneuver before systems fail completely, or a comet whose properties just happen to align in confusing ways. We lack the vocabulary to describe such objects because we have never encountered them. Our models are binary, natural or artificial, comet or spacecraft. Reality might offer a continuum, gradations we have not mapped because our observational experience is insufficient. Consider also the possibility that we are misinterpreting the scale. What if 3IATLAS is not a single object but a swarm? Thousands or millions of small particles traveling together, held loosely by mutual gravity or electrostatic forces, each particle sublimating independently, the collective producing jets that appear structured because of subtle alignments and resonances we do not understand. Swarms have been proposed for Oumuamua, arguments that it might be a fractal aggregate or rubble pile with unusual properties. The same arguments apply to 3IATLAS. If the nucleus is not solid but a loose collection, then thermal expansion, rotation, and internal collisions could create complex dynamics. Gas percolating through the structure might exit from specific regions, producing jets that persist because the structure channels the flow. Testing this requires resolving the nucleus imaging it at scales where individual components become visible. The December observations might achieve this if adaptive optics systems can compensate for atmospheric blurring and resolve details smaller than the overall coma. If the nucleus appears irregular, clumpy, showing substructure, the swarm hypothesis gains credibility. If it appears as a single coherent mass, the swarm hypothesis is ruled out. Or consider the possibility that the jets are not mass ejection at all but something else. Magnetic flux tubes anchored to the nucleus, channeling solar wind plasma into visible streams. Electrostatic discharge from a highly charged surface, ionizing surrounding gas and creating luminous trails. Optical effects produced by light scattering through dust grains with unusual properties, crystals or fluffy aggregates that create directional reflection patterns. These alternatives are unlikely but not impossible. Each could be tested with the right observations. Polarimetry to measure how light is scattered, revealing grain properties. Magnetometry from spacecraft, measuring field strengths and geometries. High-cadence imaging to detect temporal changes in jet brightness and position, distinguishing between active sublimation and passive scattering. The point is that certainty is premature. We do not have enough data to rule out most alternatives, and the alternatives we can imagine are limited by our experience and creativity. The universe is under no obligation to conform to our expectations. It will surprise us, confound us, reveal phenomena we did not predict because we lacked the imagination or the theoretical framework to conceive them. 3IATLAS challenges us to expand our thinking, to admit uncertainty, to accept that I don't know is a valid and often correct answer. This is humility, the recognition that we are early in the process of exploring interstellar objects and should not close our minds to possibilities that make us uncomfortable. The natural hypothesis is comfortable. It fits our models, requires no revision of fundamental assumptions, and allows us to continue business as usual. The artificial hypothesis is uncomfortable but stimulating, forcing us to confront the possibility that we are not alone and must reconsider our place in the cosmos. But perhaps the most uncomfortable possibility is that neither model is correct, that 3IATLAS represents something entirely outside our current conceptual frameworks, and we will need to invent new categories to describe what we are seeing. Science progresses not by confirming what we already believe, but by discovering we were wrong and adjusting our models accordingly. If 3IATLAS teaches us that lesson, if it forces us to expand our thinking and accept complexity beyond our current taxonomies, that might be more valuable than any specific answer about its nature, because the next interstellar visitor will bring new mysteries, and the one after that, and we need to be intellectually prepared to encounter the truly alien, the phenomena that defy classification, the objects that make us realize how little we truly understand. We need to confront an uncomfortable truth. Even with the best instruments humanity has ever built, we might not be able to definitively answer the questions 3IATLAS poses. Our technology, while impressive, has limits, and those limits matter when the object you are studying is millions of kilometers away, fading rapidly, and will never return. Start with angular resolution. The Hubble Space Telescope, our most capable optical observatory, has an angular resolution of about 0.05 arcseconds in visible light. At 3IATLAS's closest approach on December 19th, 1.8 astronomical units from Earth, 1 arcsecond corresponds to roughly 1,300 kilometers. Hubble's resolution translates to about 65 kilometers. If the nucleus is 10 kilometers across, Hubble will see it as a small blob, possibly resolving overall shape but not surface features, craters, vents, or structures smaller than the resolution limit. For comparison, when the Deep Impact mission visited Comet Tempel, 1-inch 2005, the spacecraft approached to within a few hundred kilometers, achieving resolution of meters. We could see boulders, cliffs, smooth plains, and active jets launching from specific locations. That level of detail transformed our understanding of cometary nuclei, revealing them as complex geological bodies, not just dirty snowballs. We will never get that view of 3IATLAS. No spacecraft will intercept it. We are limited to remote sensing from vast distances, extracting what information we can from photons that traveled millions of kilometers and arrived scattered, attenuated, mixed with background noise. Spectroscopy faces similar limits. We can measure overall composition, identifying molecules based on their spectral fingerprints, absorption and emission lines at specific wavelengths. But detecting subtle differences, trace species present at parts per million, requires signal-to-noise ratios we cannot achieve when the target is faint and distant. The James Webb Space Telescope is more sensitive than anything before it, but even Webb struggles with comets that are magnitude 12 or fainter. Radio astronomy offers the potential to detect signals if the object is transmitting, but searches conducted so far have found nothing. Multiple facilities have listened across broad frequency ranges, searching for narrow-band emissions, characteristic of artificial transmitters, silence. You could argue that the absence of signals does not rule out artificial origins, that the probe might be inactive, stealthy, or using communication methods we do not recognize. But each non-detection makes the artificial hypothesis harder to defend. Temporal resolution is another issue. Comets change on timescales of hours to days as they rotate and as solar heating varies. To fully characterize behavior, we need continuous monitoring, observations every few hours, tracking how jets brighten and fade, how the coma expands and contracts, how rotation modulates activity. But telescopes are expensive, oversubscribed, and few facilities can dedicate that much time to a single target. We get snapshots, intermittent views separated by days or weeks, missing transient events, and short-term variations that might reveal critical details. And then there is the fundamental problem of ambiguity. Many natural processes can mimic structure and organization. Rotating nuclei with multiple active vents can produce jet patterns that look designed but are actually random. Projection effects can create illusions of sunward motion when particles are actually moving in different directions. Coincidences of viewing geometry can align structures in ways that appear significant but are meaningless. Distinguishing signal from noise, pattern from coincidence, intent from accident, is extraordinarily difficult when you are working with limited data from a unique object you have never seen before and will never see again. You can build models, run simulations, compare observations to predictions. But models have assumptions, simulations are only as good as the physics you include, and observations have uncertainties. Peer review helps. Independent teams analyze the same data, check calculations, propose alternative interpretations. Consensus builds when multiple approaches converge on the same conclusion. But consensus can also be wrong, especially when dealing with unprecedented phenomena. History is full of examples where the scientific consensus dismissed anomalies that later turned out to be real and important. The discovery of cosmic expansion, the existence of black holes, the reality of continental drift, all were initially met with skepticism, dismissed as observational errors or misinterpretations. Only after overwhelming evidence accumulated did the consensus shift. Are we in that position with 3IATLAS? Is the community dismissing anomalies that future astronomers will recognize as obvious signs of something extraordinary? Or are we being appropriately skeptical, demanding strong evidence before accepting extraordinary claims? We cannot know yet. The story is still unfolding. But we can recognize that our tools, while powerful, are imperfect, and our conclusions, however carefully reasoned, are provisional, subject to revision as new data emerge or new techniques are developed. One of the most frustrating limitations is the inability to conduct follow-up experiments. In a laboratory, if you observe something strange, you can repeat the experiment, vary conditions, test different hypotheses systematically. In astronomy, especially with transient one-time events like interstellar visitors, you get one shot. If you miss it, if you make a mistake, if your interpretation is wrong, there is no do-over. This asymmetry between problem complexity and observational opportunity is maddening. We face perhaps the most important question in science, whether we are alone in the universe, and we must answer it using incomplete data from fleeting observations of objects we cannot control or revisit. It is like trying to reconstruct an entire organism from a single blurry photograph taken at a distance while the organism is running away. We do the best we can. We extract maximum information from limited photons, develop clever analysis techniques, coordinate observations across multiple facilities to build comprehensive data sets. But humility is required, recognition that what we conclude today might be overturned tomorrow by a new observation or a better model. This is why the calls for targeted missions, dedicated facilities, and increased funding matter. The Vera Rubin Observatory, when fully operational, will find dozens or hundreds of interstellar objects, giving us the statistics needed to identify patterns and outliers. The Comet Interceptor mission will enable close-range flybys, capturing data Earth-based telescopes cannot access. Proposed concepts like space-based interferometers and next-generation adaptive optics systems will push angular resolution to the limits of physics, resolving details we can currently only imagine. But these capabilities are years or decades away. For 3IATLAS, we work with what we have, aware of the limits, cognizant that our conclusions carry uncertainties, hoping that despite the challenges, we can extract enough truth to guide the next steps. The universe is not obligated to make things easy for us. It presents mysteries on its own terms, and we adapt, improvise, and persist because the alternative is ignorance, and curiosity will not allow that. Step back from the data, the spectra, the orbital mechanics, and consider what this really means. If 3IATLAS is natural, an unusually active comet with properties we have not seen before, that is important science. We learn about the diversity of interstellar objects, the chemistry of other stellar systems, the processes that shape icy bodies throughout the galaxy. Papers will be written, models will be refined, our understanding of planetary system formation will deepen incrementally. But if 3IATLAS is artificial, even if it is a derelict probe long since failed, the implications transcend science. They touch philosophy, theology, politics, our understanding of humanity's place in the cosmos, and our future trajectory as a species. This is not just another astronomical discovery. This is a pivot point, a moment where history divides into before and after. Confirmation that we are not alone, that intelligence exists elsewhere, that someone built something and sent it across the light years to visit us, or at least to pass through our neighborhood, that changes everything. Not immediately, not in practical day-to-day ways. You will still go to work, pay bills, navigate human relationships as you always have, but the context shifts. The background against which you live your life is no longer Earth and humanity alone, but Earth and humanity and them, whoever they are, wherever they came from, whatever they wanted or hoped to achieve by building probes and sending them into the void. This touches the Fermi paradox directly. If the galaxy is old, if civilizations arise and build technology and expand, then where are they? Why do we not see obvious signs, megastructures, fleets of spacecraft, communications networks, spanning the stars? The silence has been interpreted as evidence that intelligence is rare, that civilizations self-destruct before achieving interstellar capabilities, that we are alone, or effectively so. But what if the silence is not absence but subtlety? What if the galaxy is filled with artifacts, probes, relics, but they are small, quiet, camouflaged, easy to mistake for natural objects, unless you look carefully? What if we are surrounded by evidence but have been blind to it because we expected something loud and obvious, when reality is understated and ambiguous? 3IATLAS, Oumuamua, and every future anomaly force us to reconsider that assumption. Maybe first contact does not come as a radio signal or a visiting fleet, but as a rock that behaves slightly wrong, a visitor whose motion does not quite fit models, an object that makes us question whether we are seeing nature or something else. This is unsettling because it is uncertain. We prefer clarity, unambiguous answers, signals we cannot misinterpret. Reality might not accommodate that preference. Philosophically, the discovery would vindicate those who argued that life and intelligence are common, that the universe is not sterile, that we are part of a broader community, even if communication is difficult or impossible across interstellar distances. It would challenge religious frameworks that place humanity at the center of creation, though many theologians have already accommodated the possibility of extraterrestrial life into their doctrines. Politically, the discovery could unify or divide. Shared knowledge that we are not alone might inspire cooperation, the recognition that humanity is one species among many, our tribal divisions insignificant against the cosmic backdrop. Or it might intensify conflict, fear of the unknown weaponized by demagogues, paranoia about alien intentions exploited for power. History suggests both are possible, and outcomes depend on how the discovery is communicated and managed. Scientifically, the discovery would trigger an explosion of activity. Funding for SETI programs, exobiology research, interstellar mission concepts, all would increase as the abstract question of alien life becomes concrete. We would study every interstellar visitor with maximum effort, searching for more examples, trying to understand who built them, why, and whether active probes might still be functional and observing us. Existentially, the discovery would challenge our assumptions about agency and purpose. If civilizations send probes, what do they hope to achieve? Are the probes scientific, gathering data for archives on distant worlds? Are they exploratory, mapping the galaxy for future colonization? Are they warnings, markers left by civilizations that destroyed themselves, cautioning others against similar mistakes? Or are they something else entirely, purposes we cannot fathom because our minds do not work like theirs? These questions have no easy answers, and we might never know. But asking them, seriously engaging with the possibility that we share the cosmos with others, expands our thinking and forces humility. We are accustomed to being the smartest, most capable species on Earth, the ones who build and explore and dominate. Confronting the reality that someone else achieved interstellar travel, perhaps millions or billions of years ago, reminds us how young and inexperienced we are. Carl Sagan wrote that extraordinary claims require extraordinary evidence. This has become a mantra in discussions of UFOs, aliens, and anomalies. It is a reasonable standard, guarding against credulity and ensuring that we do not accept sensational claims based on weak data. But it also sets a high bar, perhaps too high when dealing with inherently ambiguous evidence from unique events. What constitutes extraordinary evidence? A radio signal would qualify, clear, and artificial, unmistakable in its intent. A spacecraft with visible hull markings, windows, antenna, unambiguously technological, would qualify. But a probe designed to blend in, built from natural materials, showing behavior that is unusual but not impossible to explain naturally, that occupies a grey zone. It might be extraordinary but not obviously so. It might be the thing we are looking for, but we refuse to see it because it does not match our preconceptions. This is the danger of demanding perfect clarity. Reality is messy, evidence is ambiguous. And if we insist on waiting for ironclad proof before taking possibilities seriously, we might overlook the subtle signals that reality actually provides. Avi Loeb argues for lowering the bar, for taking anomalies seriously even when natural explanations exist, for allocating resources to test the artificial hypothesis rigorously rather than dismissing it by default. He is criticized for this, accused of seeking publicity, of crying wolf, of damaging his reputation and that of the field by entertaining ideas most scientists consider fringe. But someone needs to ask uncomfortable questions. Someone needs to push the boundaries, to challenge orthodoxy, to insist that we look carefully at what the universe is showing us rather than what we expect to see. If everyone stayed within consensus, science would stagnate. Progress requires mavericks willing to risk being wrong, to advocate for unpopular ideas, to force the community to confront data it would prefer to ignore. Whether Loeb is ultimately proven right or wrong about Oumuamua and 3IATLAS, his willingness to publicly argue for serious investigation is valuable. It expands the Overton window, making it acceptable to discuss possibilities that were previously taboo. It forces observations and analyses that would not have happened otherwise. And it engages the public, drawing attention and interest to science in ways that dry academic papers cannot. The stakes are existential because this question, are we alone, touches the core of what it means to be human. Are we an accident, a random fluctuation in an indifferent universe, or are we part of a pattern, one instance of a common phenomenon that arises wherever conditions allow? Do we have cosmic kin, civilizations that face challenges similar to ours, that struggled and perhaps overcame or perhaps failed, whose stories might teach us how to navigate our own future? We do not know yet. 3IATLAS does not provide definitive answers, but it forces us to ask, and that asking, that willingness to confront the question seriously, is itself significant. Because one day, perhaps soon, an interstellar visitor will arrive whose nature is unmistakable. And when that day comes, we will be better prepared because of the debates we are having now, the observations we are conducting, the intellectual groundwork being laid by scientists willing to take risks and ask whether this strange rock from another star might be something more. 3I/ATLAS is fading. By the time you watch this, the comet might have dropped below magnitude 12, visible only to experienced observers with substantial equipment and patience. By Christmas 2025, it will be slipping beyond Neptune's orbit, the point where solar heating becomes negligible and activity ceases. By mid-2026, it will be gone, another faint speck among billions of background stars, indistinguishable, forgotten by all except the handful of astronomers who track its slow recession into the interstellar dark. The data we have collected, and whatever we manage to gather in the remaining weeks, will be all we ever have. No spacecraft will intercept this visitor. No future observations will reveal what we missed. The questions 3I/ATLAS raises, whether it is a comet behaving strangely or something else entirely, might never be definitively answered. We will be left with probabilities, with arguments and counter-arguments, with competing interpretations that cannot be falsified because the evidence is insufficient. This is the reality of studying interstellar objects. They arrive without warning, blaze through the inner solar system in weeks or months, and vanish before we fully understand what we are looking at. We piece together fragmentary data, extrapolate from limited observations, and hope our conclusions approximate truth. But doubt remains, uncertainty lingers. And perhaps that is appropriate, a reminder that the universe is vast and old and full of phenomena we have barely begun to catalogue. What do we know for certain? That 3I/ATLAS arrived from interstellar space, that it passed perihelion on October 30th, 2025, that it erupted with extraordinary violence, producing at least 7 visible jets, some pointing toward the sun in defiance of standard cometary behavior, that it is losing mass at prodigious rates, 10 to 30% of its total mass, enough to threaten structural integrity, that it shows non-gravitational acceleration, deviating from purely gravitational trajectories in ways that require explanation. What do we not know? Whether the jets are natural, created by subsurface ice reservoirs sublimating under solar heating, or artificial, controlled thrusters using the comet itself as propellant. Whether the sunward jets are illusions, projection effects from our viewing angle, or real streams of material pushed against solar wind by forces we do not understand. Whether the non-gravitational acceleration matches what the observed mass loss predicts or exceeds it, suggesting additional, unseen forces. Whether the nucleus is a solid body, a rubble pile, or something else entirely. The natural explanation remains the safest bet. Comets are diverse, surprising, capable of behavior we have not seen before. High carbon dioxide content drives activity at great distances and produces jets that can appear structured. Rotation and spin axis alignment create patterns in outgassing. Large dust grains trailing behind the nucleus create anti-tail illusions. Stack enough coincidences, tune enough parameters, and you can fit observations into a natural framework. But the artificial hypothesis has not been ruled out. It remains testable, falsifiable, consistent with physics, and with the possibility that technological civilizations exist and send probes across the galaxy. The lack of radio signals and the natural spectroscopic composition are challenges, but not fatal ones. A probe could be inactive, designed to be subtle, built from locally sourced materials to avoid detection. The jets could be exactly what they appear to be, controlled, thrust executed during a maneuver that will determine the object's trajectory for the next million years. We stand at a moment of maximum uncertainty, aware that we are missing something but unable to determine what. The window is closing, opportunities are passing, and soon, 3I/ATLAS will be beyond our reach, carrying its secrets back into the void from which it came. Future interstellar visitors will bring new mysteries. The Vera Rubin Observatory will find them regularly once it begins full operations. Each one will be different, each will teach us something, and together they will build the statistical foundation needed to separate common from rare, natural from potentially artificial. We are still in the early days of this field, still learning what questions to ask and how to answer them. But every beginning is uncertain, every new frontier is ambiguous. And perhaps the greatest lesson 3I/ATLAS offers is not about comets or probes or alien civilizations, but about ourselves, about our willingness to confront the unknown, to admit when we do not know, to remain curious and humble in the face of a universe that refuses to fit neatly into our categories. Are we alone? Are we being visited? Is the galaxy full of silent artifacts drifting through the dark, waiting for someone to recognize them? We do not know, not yet. But we are learning how to find out, building the tools and the intellectual frameworks that will someday allow us to answer with confidence. 3IATLAS is a chapter in that longer story. Not the conclusion, but a step forward, a data point, a reminder that the cosmos has surprises left for us. That we are still explorers, still discovering, still capable of being astonished by what lies beyond our small world. Look up at the sky in the pre-dawn hours, somewhere among the stars, invisible to the naked eye. 3IATLAS is receding. 7 jets fading, activity diminishing, the eruption ending as solar heat weakens with distance. It came from another star. It will return to interstellar space. And we, for a brief moment in cosmic time, had the chance to witness its passage and wonder at what we were seeing. That chance is ending. The observations are concluding, the data are being analysed, and soon all we will have are memories, archived images, and the questions that refuse to fade. Questions about who we are, whether we are alone, and what it means when a visitor from the stars behaves in ways we cannot quite explain. The answer might be natural, mundane, another comet with unusual properties. Or it might be extraordinary, a glimpse of something built and sent by minds that looked up at their own sky billions of years ago and wondered, as we do now, whether anyone else is out there. Whether the messages they sent, the probes they launched, the artifacts they scattered across the galaxy would ever be found and understood. We do not know which story is true. We might never know, but the asking matters. The search continues. And one day, perhaps in our lifetimes, an interstellar visitor will arrive whose nature leaves no room for doubt. And on that day, everything changes. Until then, we watch, we measure, we debate, and we wait for the next visitor, the next mystery, the next chance to learn what the universe is trying to tell us.